Hello.
Hello.
Yeah. We'll be doing some questions and we'll be finishing number theory. These are all questions from EMCs and AIME. So let's start with first one. Uh, the question is, it is known that for all positive integers k, 1 square plus 2 square up to k square is equal to k into k plus 1. This is a formula k into k plus 1 into 2k plus 1 by 6. Now find the smallest positive integer k. Find the smallest positive integer k such that 1 square plus 2 square up to k square is a multiple of 200. That is the question.
Okay.
Mm, Wait 1 second. It is not 200, it's 1200.
Oh, 1200?
Mm. Is a multiple of 1200. We have something like k into k plus 1 into 2k plus 1 by 6 is congruent to 0 mod 1200, right?
Yeah.
That automatically means that the product of these three itself
Is
also has to be 0 mod 1200.
right, yeah. So then
Now, then what?
so then 1200 is prime factorized to like 2 to the power of 4 times 3 times 5 to the power of 2. And then we know that 2k plus 1 is always going to be odd. So then that has to be some odd number out of those prime factorizations.
Mhm.
And I'm thinking from there.
If you look at these prime factors, you can write it as 3 into 16 into 25. They are 3, 16, and 25 are relatively co-prime with each other. Or you
Right.
can say that they are pairwise co-prime.
Yeah.
If your question was x is congruent to something mod 3 and x is congruent to something mod 16 and x is congruent to something mod 25. By Chinese remainder theorem on these co-prime moduluses, you can say that there is a solution and it will be congruent to something mod product of these three.
Right.
So here we already know that it is congruent to 0 mod 1200.
Yeah.
So what you should think is the reverse of it. We know that the product is coming from Chinese remainder theorem. We should try to figure out mod 3, mod 16, mod 25 what it is, right?
Yeah.
Because that will give us an idea, better idea of K, because it will
Yeah.
give us more restrictions on K.
Right.
So this fits the Chinese remainder theorem. You just have to figure out the initial A1, A2, A3 that we discussed. If you
Yeah.
can figure out that, then you will be able to say what can be K. K into K plus 1 into 2K plus 1. If we think of it as mod 3, uh, because it is 0 here, can we say it is 0 mod 3 here, 0, 0, 0? That's what I'm thinking. Zero mod 3. Can it be said that? If we look at the number k into k plus 1 into 2k plus 1, and if you think of it modulo 3, if k is 0 mod 3, the whole thing is 0 mod 3, right?
Right.
If k is 1 mod 3, then you'll get 1 mod 3, 2 mod 3, and this will become 3 mod 3, which is 0 mod 3.
Yeah.
And if k is 2 mod 3, then the middle one will become 0 mod 3.
Right.
Basically, in all cases, this thing is 0 mod 3.
Yeah.
Okay, so here we are getting a1 should be 0. We are getting x is congruent to 0 mod 3. Right?
Yeah.
In any case, it is 0 mod 3 for sure, no matter what kind of x you take.
Yeah.
Okay, if we look at mod of 16, then first of all, the question is it 0 mod 16 or not? So, is it always 0 mod 16 and 0 mod 25? It's supposed to be like that, or it can be any other integer. So, we are trying to think about the converse of the remainder theorem. So, because we know it is 0 mod 1200, can we say this?
Yeah.
So, if we apply the, like we should check from here, can we conclude that it will be 0 mod 1200? Like we can do that calculation, right? That's not very difficult. If that is true, then maybe we can go in the reverse way also. Do you understand what I'm saying right now?
Wait, what do you mean do the calculation?
What was the Chinese remainder theorem we discussed last week?
Oh yeah, it was like yeah, I get that, but do you mean like putting it in backwards?
I'm saying if we knew that it was 0 mod 3, 0 mod 16, 0 mod 25, from there obviously we can check whether
Oh.
it comes out to be 0 mod 1200.
Oh yeah. Okay. Yeah.
If that is true, then perhaps we can do the converse as well.
Yeah.
Right now we know that it is 0 mod 1200. We have to figure out whether it is 0 mod 3, 0 mod 16, and 0 mod 25.
Yeah.
If x is congruent to 0 mod 16, from there you will get k can only be 0 or 15, because you have, if it is k is 0 mod 16, then automatically the whole thing is 0 mod 16. And if k is
Yeah.
15 mod 16 also it works.
Yeah.
If you take any other like 13 or 14 or 12 or whatever, it doesn't work, because you can just confirm that by checking the product.
Yeah.
Similarly, you have to see x is 0 mod 25. When will that happen? K should be what?
Um, K would be either 0 mod 25, 24 mod 25, or or 12.
Can be 12, 24, or 0 mod 25. Now, if you think of these numbers, mod 25, if you list down all of the possibilities starting from the lowest number, K can be 0 or 12 or 24. After that, it can be what? It can be 25 or 37 or 49, and so on. You start listing out everything: 50, 62, and 74. And then after that, 75 and 87 and 99. And the next ones after that will be 100, 112, and 124. But out of all of these numbers so far, there is not a single number which is 0 mod 16 or 15 mod 16. Till here, all of these.
Right.
The first one that fits is 112. For 25, we are getting these three cases. We start by listing them out because that they will be fewer in number. And the first number that we get, which is also satisfying 0 mod 16 or 15 mod 16, that first number is 112, because
Yeah.
112 is divisible by 16.
Right.
So that means 112 is the smallest number that satisfies both the lower congruences.
Yeah.
And we don't need to worry about this one, because in any case, if k is any mod 3, it will work that the whole thing is 0 mod 3.
Right.
So 112 is the solution of these two congruences, and that will make sure that it will satisfy that it is overall the product is going to be 0 mod 1200.
Yeah.
Do you understand what I'm saying?
Yeah, I understood.
The point is that we are doing Chinese remainder theorem, but the opposite.
Right.
We know that it is 0 mod 1200. From there, we are trying to figure out how can we get it as 0 mod 16, 0 mod 3, and 0 mod 25.
Right.
And what is the smallest k that works? The best way to do that is to start with the highest modulus, and from there, okay, we figured out it has to be 0, 24, 12, and for 16 it was 0 or 15. And from there, we just list out and see the common solutions.
Yeah.
Okay. Next question is, let 2 power 1110 be congruent to n mod with 0 is less than equal to n is less than equal to 1111. Find n. You should spot first of all that 1111 is 11 times 101.
Right.
If you don't split it, there is nothing you can do. These are both prime numbers.
Oh, so do you break it up and then use like Chinese remainder theorem to solve it?
How will you break it up?
Like, would you say that then 2 1 1 1 1 0 is equal to n mod 11? Wait, no, you can't say n. Yeah, yeah, you can n mod 11, and
No,
then
we can't say for sure it is n. You have to
so then
check whether it is what.
yeah, so it'd be a1 mod 11, and then a2 mod 101.
From here, we know how to combine, right?
Yeah. So
You have to first find A1 and A2.
yeah.
What is 2 power 10 congruent to how much mod 11?
1
Hmm.
mod 11
Why?
because of the Fermat-Little theorem.
Right. A and n are coprime, then 2 power n minus 1 or a power n minus 1 will be congruent to 1 mod n, right?
Oh, wait. Yeah, so does that mean then n is just 1?
What do you mean n is just 1?
Like because
This is not a
it's
prime number.
oh, right. And 11 is. Yeah. So
It
then 2
doesn't
to the
work
power.
for not prime.
Yeah.
If you raise this result, if you raise it to the power 111, you'll get 1110, right?
Right. Yeah.
So we got easily that this must be 1. Similarly, what is 2 power 100 mod 101?
Same thing. It's like 1 mod 101.
We need 1110. We cannot go to 1110 from here directly, but we can raise it to power 11, right?
Yeah.
We can say 2 power 1100 should be 1 mod 101 by raising it to the power 11.
Right.
So this number is basically 2 power 1100 into 2 power 10.
Right. And we
So
know 2
if
power 10. Yeah.
we know 2 power 10 mod 101, that is equal to 1024 mod 101. So You can just divide 1024. 101 into 10 will be 1010. So 14.
Yeah.
2 power 10 is 14 mod 101 and 2 power 1100 is 1 mod 101. So obviously this will be 14, right?
Yeah.
So now you have both the values. We are using Fermat's little theorem and raising it to powers and then figuring out A1 and A2, right?
Right.
So we are getting this is A1, this is A2, and now we have to find N. Now you have to apply Chinese remainder theorem and do the process that we had learned.
Yeah.
Basically, something like this we are getting, right?
Yeah.
Now we just have to find what K is. So here 9 mod 11. The numbers will be like 9 and 20. Keep adding 11, 31, and so on, right?
Right. Yeah.
40, 51, 62, 73, 84, 95, 106, and so on. So it will be okay, it will be annoying, but we just need to select what should be the K so that this is a multiple of 100. We need a multiple of 101 to appear here. So
Yeah.
that's how we can cancel 101. So we'll keep doing this a little bit. 117, 128, 139, 150, 161, 172. So 200, 194, 205 is coming. 205. So it was 106 and then 205. You're adding 99s. It will be 304. But that is still not resolved by 101, right?
Yeah.
Then it will be 403, then it will be 502 and 601. Okay, so you'll get 700 and then 799, 898, 997 and 1096. 1096, 94, 1194. Getting multiples of 99. 9 mod 11. We have to check whether any of the numbers 202, 303, 404, 505, those appear or not, right?
Yeah.
Okay, maybe the better way to do it would be to start putting K mod 11. So think of K. K has only 10 choices, 0 or 1 or 2 till 10 mod 11, right?
Yeah.
That will be a faster way to do it, because then you will just check whether the product is becoming 9 mod 11 or not, right?
Oh, right, right.
Because the direct way from this side is going to take too long.
Yeah.
We will say K is 0 mod 11, then 101 is, it is not 9 mod 11. So K cannot be 0 mod 11. K cannot be 1 mod 11 also. If it is 1 mod 11 also, it doesn't work. Because 9 mod 11 is basically, what are the numbers that are 9 mod 11? Near 101, 99 is 0 mod 11. So 9 mod
10,
11 is 108, right?
yeah. 108.
So it cannot be 1 mod, can it be 2 mod 11? K. So that will make it 202. 202 mod 11 would be how much? 110 and then 92. So it is 4 mod 11, right?
Right.
So that doesn't work. So we have eliminated K cannot be 0, 1, 2 mod 11. Let's look at 3. So it becomes 303. So
Hmm.
220 and then 83. So 83 is basically 5 mod 11. No, 6 mod 11, right?
Right.
So that is also not working. Do you understand what I'm saying?
Yeah, yeah, I understand.
4, then it is 404, and for that you will say 330 and 74. 74 is how many mod 11? 8 mod
Oh,
11. So 4
yeah.
also doesn't work. 5 means 505. That is 440 plus 65. 65 is 10 mod 11, right?
Yes.
So that also doesn't work. 5 doesn't work. So 6, you're getting 606. And that would be 550 plus 56. 56 is 1 mod 11.
Right.
7 is 707, which is 660 plus 47, which is 3 mod 11. 47 would be 3 mod
Yeah.
11. 8, 8 is coming 808, and that is 770 plus 38, which is again 5 mod 11. The product is
Yeah.
becoming 5 mod 11.
Yeah.
And
Yeah.
finally 9. K is 9 mod 11. That will be the only way it works, I think. 909, you get what?
880.
880 and 29.
29, yeah. So 7 mod.
Wait, so if K is 9 mod 11, how is it not working? K is 11J plus 9. Oh, the 9 is ruining it. With 101 it gets ruined. 909 is 7 mod 11. Right?
Right.
Okay. And if k is 10, then it becomes 1010, 990, and 20. So again, then it is working, right?
Right.
When k is 10 mod 11, in that case you are getting 1010, and
Yeah.
in that case you are getting 9 mod 11 as the answer.
Uh, yeah.
Because 990 plus 20, and 20 is 9 mod 11.
Yeah.
So it works for k is equal to 10, for example, and basically k should be 10 mod 11, right?
Yes.
The lowest number would be 10. In that case, you will get 1010 here, and that will fit the whole thing, right?
Yeah.
So, okay. So you are getting now this solution is 1010 mod 1111. No, wait, that was our k. What was our x?
X was 101K plus 14.
K was 10, right?
Yeah.
So we are getting x is 1024, right?
Uh, yeah.
So our answer is it is 1024 mod 1111.
Yeah.
Do you understand what is happening?
Yes.
We are solving, first we found the two congruences, then we are trying to solve the congruences. Here it was slightly annoying to do at this stage, but we figured out that it has to be 10 mod 11. K has to be
Right.
10 mod 11 for the overall thing to become 9 mod 11.
Yeah.
Okay. The next thing is this problem. In base 10, the number 2013 ends in digit 3. In base 9, the same number is written as 2676 base 9 it is, and ends in digit 6. Ends in digit 6. For how many positive integers b, for how many positive integers b does the base b does the base b representation of 2013 end in the digit 3? Okay, they have to end in digit 3. Your options are 6, 9, 16, and 18.
Okay.
One more option is there, 13.
Oh, okay. Is the answer 13?
Hmm. Why?
So what I did is that because it says it has to end in the digit 3, and for any binary number, the units digit, it's always like b to the power 0. So it's basically 1, and you want a 3 to be there. So that means your number 2013 has to be equal to 3 um plus uh b times some number. So it has to be 3 mod b. So that because the rest of it is going to be divisible by b, and then you have that plus 3. Yeah, and then you get 2010 is 0 mod b because you subtract. So that means mod b has to be like um something that divides 2010, so a factor of it. And then if you do the prime factorization of 2010, you get 2 times 3 times 5 times 67. And then from that, you can do the number of factors, which is 16. But then you can't have like base 1, base 2, and base 3 because you can't write the number 3 in there. So you have to take
Hmm.
3 away. And then you get 13 left.
The digits have to be smaller, or the base has to be bigger than 3. So you
Yeah.
cannot have divisors 1, 2, and 3.
Yeah.
Okay. Next one is find the remainder. Find the remainder when 12 to the power 2011 plus 11 to the power 2012 is divided by 7. You should start by looking at Fermat's little theorem. A power 6 will be congruent to 1 mod 7, right?
Right.
If A is co-prime to 7.
So then 11 to the power 2012 is also 1 mod 7.
We know 11 power 6. We can't say anything about 2012, right?
Oh, right, because it's on a multiple of 6. Okay, yeah.
We also know 12 power 6
Yes.
because both 11 and 12 are co-prime with 7. So we can
Right.
apply Fermat's theorem to both of the cases and get this much at least.
Right.
After that, it's the matter of like managing the power, how to get close to the power, right?
Yeah.
335 into 6 is how much? 335 into 6. 0, 1, and 2010. So we know already if you raise it to 335 power, you get 12 bar 2010 is congruent to 1 mod 7. Right?
Yeah. Right.
So obviously 2011 would be 12 mod 7, which is 5 mod 7.
Yeah.
Similarly, 11 part 2012 is like 11 square you're multiplying to 1, right? So it is
Uh,
11 square mod 7,
yeah.
which is basically 121 mod 7. So 70 and 30 and 21, 51. So 2 mod 7.
Right.
So you are getting 5 mod 7 here and 2 mod 7 here, which makes it 0 mod 7. Do you understand what I'm saying?
Yes.
Okay. Uh, okay. So two problems you should try. First one is this one. The smallest three positive, the smallest three positive proper divisors of n are d1 less than d2 less than d3 so that d1 plus d2 plus d3 is equal to 57. Find the sum of possible values of d2. That's the first question, and you can try that later after the
Mhm.
class. The next
Okay.
question is determine all positive integers a such that a is less than 100 and a cube plus 23 is divisible by 24. So try these two problems as homework,
Okay.
and I think we are more or less done with the number theory portion at least. Like now you just have to practice your AMC papers and all the number theory problems there.
Okay. Yeah.
Maybe we'll do one more class, Thursday's class, and then after you come back, you were going on some vacation or something, right?
Yeah.
So Thursday's class will also be number theory, and we'll do problems, and that will be the conclusion. And after that, after 18th, when we resume, it will be different topics.
Okay. All right.
Okay, fine.
Yeah. All right.
That's all for now then.
Thank you.
Bye.
Bye.